Good evening. Okay. It's pretty hot. It's pretty hot in Japan, Tokyo right now. I'm running a air conditioner right now, so it might be a bit noisy here. Okay. Well, hopefully you can hear me. Let me get started. So hello, this is Junichiro Horikawa, and this is the live stream for Houdini tutorial. It's called as Houdini Algorithmic Live. This is 142nd episode. The topic for today is to create kind of an aggregational system based on a simple polygonal geometry, which is called a truncated octahedron. Right. So it has some nice features. This shape, truncated octahedron, has some nice features that it can pack as it itself in a specific grid, like these. So I want to use this feature of this geometry to create a specific grid or network for this geometry, and also creating some growth simulations based on these truncated octahedron, which is going to be aggregated by time, creating some kind of a nest-like shape in the space. Now this has been inspired by this image here, which I saw it like few years ago, like 10 or 20 years ago on net. I think it's one of the architectural project by someone in US. Not sure, not really sure where this come from, but I saw it on magazine a few years ago, like 10 or 20 years ago. So basically it's pretty close to this project. What I'm going to do is to try to simulate this kind of structure using Houdini and try to create this structure automatically. Okay, so let's do this. Okay, so the steps that I'm going to take today. First of all, I'm going to create a single truncated octahedron procedurally, like this one. Then I'm also going to create a grid, a network for this truncated octahedron to be packed as a point and lines, so that you know where in which direction it connects to the neighbors. Then after that, I'm going to use a solver to calculate, set the starting point for the growth, then run the simulations to create a connectional network, which then can be used to place the cells, the polygon on top of those network. And that's pretty much it. Yeah, simple as that. Okay, so that's what I'm going to try to do today. It's pretty simple geometry, so the idea itself could be really simple, but then I thought, since the grid is pretty interesting, if you replace the geometry, the octahedron, the truncated octahedron itself, with other geometry which could be connected with the same grid, then you might be able to create some interesting structures or networked structures. That's what I was thinking. But as a starter, I think this is a good idea to just go with the original geometry. Okay, so let's start creating the truncated. Wait, let me just turn off the VPN. I don't need this. Okay, so let's check how this geometry is being made. And I think there was some info how this could be created. Like if you look at this wireframe, you have hexagonal shape on the corner, 1 2 3 4 on the top, 1 2 3 4 on the bottom, and this, the center of this hexagonal polygon looks like it's at the corner of the cube. Okay, and by placing the hexagonal shape on the tip of the cube, on the point of each cube, eventually you'll get these squares in between these hexagonal shapes. So my idea here to create this shape is to first place these hexagonal shapes on the corner of the cube, then let these squares be made automatically. So let's try that out. So I'm going to first create a cube and try to place the hexagon on top of each point with specific angle. Okay, and in terms of angle, you could use copy to point network, copy to point node plus normal directions and the up directions to control the angle. So let's first create a normal. For points, okay, and then let's also create a hexagonal polygon using circle node, made the division to 6, so that will be hexagon. Let's try copying this geometry to each point on the cube with the normal updated. Okay, so in terms of the perpendicular directions of each hexagon, it looks fine, but I also need to fix this rotation in these axes. So for that, I do need to set another vectors, which is a up vector. So let's set the up vector addition to the normal vector. So I'm going to create a point wrangle to create the up vector, and in this case I'm just going to try to set the up with the y positive direction and see what's happening. And now it already looks promising like this. So now it seems like what I just need to do is to set the correct size for each hexagon so that you can pretty much fit it like a truncated octahedron. So how do I decide the size? Okay, now if you look from the top view, I think you could estimate it pretty easily, since the let me draw up. So you have a square like this, right? And what you need to define is the radius of this hexagon, which is these r. Okay. Now you know that currently the size of this cube is 1 by 1 because I didn't change that size, it's a default size, meaning the size from the center to the edge is 0.5 if you look from the top view. So the radius of the hexagon can be estimated if you know that this is 45 degrees. This r cosine 45 degrees is 0.5. Okay, so meaning if you divide 0.5 by cosine 45, then I think you'll get the radius of this hexagon. So let's see if that's true. Okay, so 0.5 divided by square root 2. Nope. Actually, this is this actually, if you look at the circle, you might need to multiply this by 2. Yeah, it looks fine now. Now, let me try with the cosine. Okay, so 0.5 divided by cosine 45 works. So cosine 45 was 1 divided by root 2, was it? Okay, so here it is. Now the size looks correct to me. And now I think it now touches the edges. Then you could then fuse it and close the hole with something like polyfill, and you could easily create a truncated octahedron. Okay, looks good. Now let's recompute the normal with the vertices, something like 30 degrees. Okay, looks good. Okay, now let's now create the grid in order to make this polygon to be filled without any spaces. Okay, which is pretty easy as well. If you check again the Wikipedia, this itself is a square grid on one side, and on the next row it's shifted half size of the grid on shifted a half size on x and y direction, and you have these small hole here which is the same size of this square, so you can just fit another cells within these spaces like that. So it's pretty easy. I mean, pretty easy to create. You just need to copy these geometry to x directions as well as y directions on the first row, and then shift these on these z directions. And for even numbers and odd numbers, you could just shift half size of it to x and y. So let's create those grid with the point. I'm gonna use a detail angle, and I want to make sure if I know the size, and the size of this cube is 2. Okay, it's the size of 2 on x, y, and z direction. So let's say I know the size, which is related to this box size. Multiply by 2. Okay, I think it might be a good idea if I change the size of the box. I might also want to change these radius for those hexagons. So if I change the size of these boxes, I should recalculate the radius here, which is the box width multiplied by 0.5 divided by cosine 45. Okay, now that works. Okay, then let's create the grid. Make sure you make it as a detail, and let's define the number of cells in X, Y, and Z direction. Okay, and create a for loop for these. For X, for Y, and for Z. Okay, so within this loop, I'm going to create a points as a three-dimensional grid. Okay, so for the X direction, the X coordinate will be just a simple X number multiplied by the size. Okay, as well as for the Y. Now let's try visualizing this as a point. Let's check with the 2D grid first. Okay, do I see it? Okay, forgot to. I had to make this X being multiplied by size multiplied by I instead of X num, because X num is just a total number. Okay, so now I have those grids as 2D. Let's see if I can place grid on these points and see if it can fit together. I'm going to use copy to points. Okay, looks good. Now for the next row, you could just copy all these grid, 2D grid, and shift half size to the X directions and Y direction so that it can fit in this hole here. So for the Z, the size step for the Z direction is half size of this original size here. So Z is T multiplied by size multiplied by 0.5, and you also need to shift X, Y, and Z. So T modulus 2. So you calculate the remains of the T value, the Z value, the row number, then multiply by the half size of size to shift. Do the same for the Y. And set this to Z. And now you are already having these packed geometry. Easy as that. Okay, let's see if, okay. This has to be Xenon. Okay, looks good. So if I make this to 10 by 10 by 10, the z size is a bit z size looks like a half size because you're multiplying by 5 here, so might be a good idea if I just multiply by 2 here, just to make that it looks square, or it looks cube in the same numbers. Okay, looks good. So it's time I create the network, in which direction the points is going to be connected based on this grid. Okay, so let's create a network. What I mean is I want to create a connection between the center points of the cells to other neighbor points, so that I can use these lines as a network line, which I can then later use as a aggregational path. Okay, so in order to do that, I think there are a bunch of ways you could do that, but what I'm going to do is to create a network right here from the geometry itself, then copy it to each point with these copy to point, then just use it as a network. Oh hey, hello Nobunaga, thanks for the content severely in the day. Thank you for the super chat, and thank you for the kind comments. Okay, so let's create a network. From this geometry, what I just need to do is to create points on the center, then creates a point on each center of these primitive, and create it as a line, and multiply by 2 in terms of the length, so that it can connect to the neighbor cell. So let's do that. I'm gonna use primitive wrangle to get the center of each primitive, which is at P, and I'm going to create it as PT1 or PT2, and make it as new point. And in terms of the PT1, I'm gonna create one point on the center, which is 0, 0, 0. Okay, so I want to connect these 2 points together. Now, as I said, I want to multiply the lengths. I want to multiply the lengths of the line by 2, so that it will have a connection between one cell to the other neighbor one. So I'm going to multiply the current position, the current center point by 2, so that I can detect the neighbor points, neighbor center points. Okay, then I'll create a line between them. Yeah, like that. So this lines is going to be the base connection, base connection, which connects between one cell to the other cell. And let's give these lines some attributes, so that you know which one stands for the hexagonal connections, and which one stands for the square connections, which you might want to use it to when you are doing the aggregation, to prioritize in which direction you want to go and which connection you want to use. Okay, so in order to define, in order to know which ones you are using, square or hexagon, you might want to count the numbers of each primitive first. So first get the list of points from the primitive and count it up, and if the count is equal to 4, then it's square. So set prim group to the line square Otherwise, it should be hexagon, so give the hexagon group. Okay. Now, you don't really need the faces anymore, so you can just remove it. Okay, so now you are only having these network. Now let's fuse it so that you are going to have only one center. Let's call this single cell connection. And what I am going to do is to copy these network to the grid points, which will create this massive connection between the points, which looks pretty loud, pretty noisy, but it's pretty useful in the end. And it's not that heavy. And now there are some duplicate lines because you're using multiple double lengths for each cells. So just purge it using convert. First of all, fuse it, then convert it into line. Then you can purge all the duplicated lines. So previously it was around 28,000. Now it's around 15,000. Okay. Now that I have a network, I think it's time I create some basic aggregational simulations at this point. Now let's see what I need to do first in order to create a simulations. The first thing I would need is to set a starting point in where to start the aggregation, the growth for the cell. What I want to do is to set some start point. And using a time step to choose in which direction it want to grow. In the sample that I showed you previously, it just grows in one directions. In one way, but you could also add some additional conditions to branching and some conditions, which might be also interesting. I also need to tell some conditions in which directions it should go. I don't want to pack in one place like that to create some massive chunk, but I want to have more like a branch-like shape. So need to create that kind of conditions here. So let's see how I can do that. First thing first, I am going to set the starting point. It could be single, it could be multiple. Let's try with the multiple points so that it's more versatile. Okay, so I'm going to choose some random points in the space just by using something like attribute wrangle with the detail. Then specify number of points you want to choose as a starting point. Let's say you want to have like 4 starting points. Now what you want to do next is to randomly pick 4 points from this grid. So let's create a loop for this number. Then create random index of the points and pick that as a starting point. So the total number of points can be retrieved using endpoints. And by multiplying by some random value based on the iterations value with some seed, maybe you could get a random value for each loop iterations. And let's make it floor so that there will be an integer value. Now using an index which is same as the point number, let's set point group to set it as a tip point for the growth or aggregation, which is always going to be the group where you want to grow from, not the PT num but index. Now let's add additional group, set it as something like AGG aggregation, to know that it's been already visited or being used as a growth, which is more like a history. This is the current group, this is more like a history group. Okay, and let's check where that is using the color node, see if I'm setting the correct points. Okay, so I do have random 4 red points in the space. Okay, so these are going to be the starting point for the aggregation. Okay, that sounds good. Now anything else? Okay, well, I think I'm ready to go for the simulation, so let's group this up and let's do a subsolver. See what I can do. Okay, so inside a subsolver, which is going to be pretty simple, but what I'm going to do is to look for the tip points, the points which has tip group, and decide in which direction it wants to go. And the important stuff here is to choose the direction, and the important thing is to choose what condition do you want to have in order to choose the direction. Do you need to look for the how many points are being already connected on the neighbor points, or do you want to go downward, upward? Do you want to use the hexagonal connections or square connections, and so on? So let's take that in mind and choose some wise direction or interesting direction. I'm gonna call this aggregate, and let's make sure that this only works on tip points. Okay, now it's time we do some coding here. So first of all, I want to get all the possible neighbors. So let's get the neighbor points using point neighbors function. Now from these neighbors, I want to choose in which points I want to choose for the next direction. So what I want to do here is to calculate some weight, like based on the conditions. For example, if it's hexagonal connections, you have more chances to go to that direction than square. If it's going downward, you have more chances than going upward, and so on. So you want to calculate, you want to have all these weights, and based on these weights you want to choose in which directions you want to choose in these chances based on these weights. So it's more of a probabilistical calculation. Okay. And in order to do that, first thing first, you need to calculate some weights for each neighbors. So let's do that. Get the neighbor points. And let's also get the neighbor position. Okay, now let's also get some informations like if it is a what was it, square connections or hexagonal connection. Now these informations are inside the primitive group like these, so we need to get those primitive informations from these points. Okay, so I was wondering if it's possible to get the primitive number from the points. Maybe instead of using the neighbor points itself, it might be a good idea to just get the neighbor, the associated primitives instead of using neighbors, but I am going to use a point prims, which then you can get all the connected primitives to this current point, which is, I think it's more useful because you could also get the endpoints, the neighbor points, as well as the primitive information. Okay, so let's use this information. So and once you have the neighbor primitive, let's get the end point number here, which is first of all, you can get the neighbor prim points from prim points using the neighbor prim. Then one of the points included in this array is the pt num, so you can remove the value pt num from this array, and the only points left is the one that's neighbor to yourself. Okay, so like that. That's a bit of, oops, maybe some typos here. Okay, so it's a bit of coding, but you get more information than using neighbors, so I think it's pretty useful. Okay, now you can now get whether it's hexagonal connections or not. So hex connections in prim group hexagon neighbor prim. Okay, I guess I don't need to get the squares because it's either a square or hexagon. So okay, now let's try to use these informations, either hexagon or square, to create a weights. So let's say I want to have more chance to go to the hexagonal direction, meaning if it's either hexagon or square and this is the point, I want to have more chances to go to this directions than this directions. Let's say like 80% to this direction, 20% to go to this direction. Okay, So let's see how we could do that. So I want to create a weight here, right? So if hexcon is equal to 1, meaning if it is hexagonal, if it's hexagonal directions, I want to create a weight starting from 0. If it's equal to 1, let's make it 0.8, like 80%. Else, %. Okay. And do this conditions for all the primitives. So I need to gather all these informations, all these weights informations as an array for each neighbors. So let's create an array called weights and create an empty array, append this weights to here. Okay, and let's check what we got. What are we going to get here? Spell mistake. Okay, so let's check the geometry spreadsheet for a tip point. And what do we have as an array? So we have something like these. So this is probability in which direction the connection we're going to choose as a connection, as a direction for the next step. So for the first cell, you have 80% in this direction, 20% in this direction, 80% in this direction, and so on. So somehow you want to use some random value to choose either one of them, either one of the connections randomly, but with these weight. Okay. So my idea here is to make these numbers normalized, something like for example, if it's 0.8, 0.2, 0.8, you first add all these values together. In this case you get 1.8. Okay, and if you divide all these weights by 1.8, you get 1 as a result, right? And if you divide each one of the values by 1.8, you're going to have something smaller, but when you add all these up together, you always get 1. So by having these values, the weights is going to be normalized, and it will be more easier for us to use it with some random values using random functions to choose which value to be chosen with some randomness. So let's normalize these. And in order to do that, you need to have a sum of all the weights. So I'm going to create another float variable, and for each step in the loop, I'm going to add the weight to the sum weight, and then in the end you're going to have the sum, the total value of the weights. Then after leaving the loop, I want to have another loop for a weights, to divide each value by sum to normalize. Current weight divided by the sum weight. Sum. Okay. Now let's check that value. Okay. Norm weights. Check how this looks like. Okay, now it looks like these. And if you add all these values together, you always get 1. If you add all these values together, you get 1. It's pretty useful. Now, in order to use it with a random value, to choose the probability, to choose the possible direction, what I can do now next is to know what kind of value you get out of these functions, random. Now, when you use random functions, you always get value in between 0 to 1 as a float value, 0 to 1.0. Okay, and the chances you get 0 to 1.0 is all equal. You could get 0 or you could get 1 and same chances. But I want to change these chances to choose these values based on these values. So what I'm gonna do now is to modify these values. For example, if I have 0.44, 1.11, 0.44, I'm gonna create a value something like this: 0 to 0.44, 0.44 to 0.55, 0.55 to 1.0. You creating some kind of a range, which is, if you have a 0 something right here, it's from 0 to 1.44, and from 1.44 to this value plus 0.11, which is 0.44 to 0.55, and 0.55 to the final value by adding 0.55 to 0.44, which is somewhere around 1. So you get this range. And if you subtract this maximum value by minimum, you get these ranges, these lengths here. So what I want to do is to create these ranges: 1, 0.0 from 0.44, 0.44 to 0.55, 0.55 to 1. And by creating these ranges, if you have a random value, for example, if you say 0.5, this value is in between these small range, which is in between 44 to 55. So in that case, you could choose the square direction. If the random value is 0.3, which is in between 0 to 0.44, so you have like 44% to choose this one, then you can go to this direction. If the random value gives you 0.8, then this is within this range, so you can go to this directions. So this is how you can control the probability using randomness and the weights, okay, which is kind of a versatile idea, could be used for a lot of situations, I think. So I think it's pretty useful to think this way. So let's create these range value from these weights, which is not that hard, I think. So let's do that. First thing first, I need to have the starting point of this range, which is 0, okay, from 0 to the first value. So let's call this float prev val, starting from 0, or prev weight. Okay, now the prev weight is going to be the minimum of the range. Let's say this is the minimum of the range, and I want to have the next weight, which is going to be the maximum of the range, and that is the same as this weight here. So actually not. This is a prev weight plus the weight, because for each range you have to add this normalized weight to the previous weight. Okay, and in the end of the loop you have to update the prev weight with the next weight. And in between these, this is where you're going to create a random value and compare with this range together with the prev weight and the next weight. So let's create some random value. Random using, I don't know, I multiply by some additional seed. Okay, and check whether this random value is in between this previous weight and the next weight. If it's so, then that's the direction you want to choose. If it's not, you can skip to the next iterations. If the random value is more than prev weight, as well as less than next weight, then this I value, this I value, which stands for this direction, the index of the primitive, is going to be the one that you want to go for. Okay, so let's say chosen index, starting with the minus -1, and chosen index is going to be I. And after you have chosen the direction, I think you can just leave the loop at this point, because you no longer need to calculate after that, I believe. Okay, and let's see if this is going to work. We need to check if this is going to work. Now let's now that we have chosen the index, we need to get the point information, which corresponds to the neighbor primitive number. So we kind of need to have that array as well, array for the neighbor points. So let's create that one as well. Okay, append and the final neighbor point that we're going to use is chosen index here. And let's see, what do we have as a chosen index? as well as the neighbor point. Let's just make sure that the chosen index is somewhat varied. Now I think I need to set some seed. Now I think I have some problem here because everything here is 0. Oh, I do have some changes. Ah, okay. It only works on the tip point, so that makes sense. Okay, so seems like it does chosen some random values based on the weights, I think. So let's try this out to see if I have more chance to go to the hexagonal direction rather than the square direction. So currently 80% goes to hexagonal direction, 20% to square directions. I want to check if that's the case. Okay, so now that I have chosen the next point to be moved, what I need to do now is to set this point as the next tip and make the current tip to 0. So set point group current one to 0 and set point group ptnum to 1. No, not the ptnum, but neighbor point to num. Now there is a chance that we couldn't find any anything on the next neighbors to go, meaning if the number of primitives right here is limited to 0, then there are no chances to go anywhere. So in that case, I shouldn't add any tip points for the next point. So we need to have that conditions set. If the chosen index is -1, meaning this hasn't been used, then you should stop. I'm not sure if I can use return here. Yeah, maybe. So this will terminate the code at this point. Okay, so let's see, this is gonna work. Now one thing I wanna also make is to ignore the point which has already been visited as a candidate to go for the next direction. So in that case, I need to have another group, which was AGG aggregation, the history group. So let's have that as additional conditions. Int AGG in point group for the neighbor point. If only if AGG is equal to 0, then you can add these points to the array. Okay. And that means you also need to add this aggregation to the next direction, just as the tips, so that it can be used as a history. And you don't need to delete it here because it's a history, you want to keep it. Okay, so this is the basic structure of the conditions. Let's see if it's going to work. First of all, let's color the AGG and see if it's going to grow over time. And it did, but it stopped at some point, as you can see here. Okay, so let's see why is that. Okay, what I'm going to do, I'm going to first get only the points where you have AGG points. Okay, and copy the original geometry that I have here, truncated octahedron, to these points, and see how it has been grown. And you can see from the first step, it chose the hexagonal direction, just as we assumed. Chosen another hexagonal direction and been choosing, but somehow it just stopped at this point. Now there are more chances to go as a direction, so that doesn't make sense to stop at this point, so maybe something is wrong here. So it's not growing anymore here. But at least the chances to go to the hexagon seems to work. Let's try to change the chances so that you have more chance to go to the square direction. So if I make the hexagonal chance to 0.1, square to 0.9, let's see if it's going to go to the square directions instead. Now, yeah, if you look at here, in the first step it goes to the square directions. In the next step, now this one chooses hexagon, which could be possible. This goes to the square, but the weird thing is that it just stops so soon, which is not as I expected, so something must be wrong here. Let's check the tip points, the current tip points. Okay, so it's all 0. You do have aggregation. So something must be wrong with these conditions here that I have created. Okay, so let's just check it out. Let's go, and I think it will be easier to debug with just one starting point, so I'm going to make this the 1. So you just need to follow this points. Okay, and let's check this out, shall we? So this is the starting point. Okay, now in the next step, let's go to the end and visualize the tip point here. Now it doesn't seem to change, does it? It's not really moving. So let's see if I really have a candidate for the next step. So what I need to check is these norm weights. Do I have a normal weights here? If it's empty, then that's a problematic. You have to have some options, but now that I think, since this has no square directions, but anyway, you do have chances to go to hexagonal directions even with small percentage, so it's not it should not be a problem. Okay, so let's check the current tip point. Let's remove these part for now. Okay, where's the tip points? Let's go to the first frame. So, okay, so you do have several directions for next one. Okay. And let's also check the neighbor points list if I have that or not. Okay, I do have it, so I have 3 options to go. I have 3 values for the normalized value. Yeah, so somewhat 10% to go to this direction, 80% to go to this direction, 10% to go to this directions. Okay, sounds good. And what's the chosen index? The chosen index. Okay, so this is the problem. Somehow what I did here is wrong. So this it means I have never okay. The problem is this randomness must not change on each loop, but it has to be fixed with for each point. That was the problem. Okay, of course. So it has to be based on the point value. It should not change within the loop, or you have chances that it never meet with these conditions. Okay, so that was full of me. I think this will now be okay. Okay, so let's okay, now I have these index right here. I should be able to have all the rest of the code worked out. Okay, so let's see. If I play it, okay, now it grows. It did stop at some point, but there is a chance that there are no more ways to go anywhere. This is more like a dead end, so there are no neighbors anymore, so maybe that's the reason why it stopped. Let's see if that's the case. Okay, so yeah, seems like so. And you can see that as much as possible it chooses the square, maybe. Well, you do have chances to choose the hexagon as well, but yeah, it still tries to go to the square, I think, but in the end it stops because there are no more neighbors available. Now another condition I would want to give to this one is to avoid having too many connections for each cells. Currently, like, one cells have more than 4 connections maybe. So let's say I want to reduce the number of cells to be connected for each point. Let's create another conditions here. Now in terms of the choice whether hexagon or square, let's say I want to choose hexagon 80%, square 20%, and I want to check if the neighbor point that I'm going to choose has already more than 3 connections. If so, I want to skip that. So this should be done somewhere around here before adding the neighbors. Okay, so in order to check that you need to look for all the neighbors for this neighbor point and count how many aggregations it has as for neighbors. So int nay nn nay pts for neighbors at this neighbor point, and then loop through all the points inside this neighbors of neighbor points, which is a bit confusing. And check if that neighbor contains aggregation or not. By checking in point group HEG and PT. Okay, so if let's create a count. If this is equal to 1, count, increment the count. Now, if the total count that found on the neighbor is more than 3, then just skip it using continue. Okay, let's see what happens. So hopefully we're not going to get too packed connections with this. Oops, now it just finished at this point. Seems like couldn't find better way to go. Okay. Yeah, so it just ended at the dead point, the dead end. Now maybe I could have another I could have another weights as a chance to go to the points where you have more possibilities, more possible branches in terms of the directions. Currently, this point only has, I mean, this point doesn't have any neighbors, right? So probably I could count up the possible neighbors to go and use that value as a weights as well. So more possible neighbors, more probability you want to go, you can go to that directions. I think that might make sense. So to get that, you could use these loops that I have just created, which you are counting the number of aggregations. You could also count how many points are not already aggregated or used for the aggregations. So let's rename this as and count AGG for this one, and I am going to have another count and count free. So if this else, I can increment the free, and more free directions you have, more possibilities you want to go to that directions. Okay, and I want to add this value to the weight somehow. So I need to consider the balance between the current weight, which is based on hexagon or e square, which is already normalized. So it'll be a good idea to also normalize this n count free value, which is currently an integer value. So in order to convert this into a normalized value, you need to know what's the maximum connection you could have for each point. So from this point you have 4 hexagon and 4 square connections, which in turns you have 8 possible connections. So the maximum value of this integer could be 8. So the weight free weight, I'm just gonna call it free weight, is going to be n count free divided by 8. So this is going to be the normalized value in order to check if it's more possible to go to that more branches you could go in with that direction. So now that I have this value, and let's also rename this value so that it's based on the connection. Okay, so I have now 2 weight value. The final weight value could be a multiplication of these 2. Wait a minute. Which means I'm going to consider both possibilities. Okay, now let's see what we get as a result. Hopefully it's gonna go to the center as much as possible. There you go. So now it's going to search for more, it could search for the neighbors which has more possible connections, and you're going to have more chances to go inward. Okay, so looks better than before. Okay, now it ended at some point, but it's fine. Okay, now maybe I could add additional conditions to this one. After it had stopped at the dead end, maybe I can choose additional, I can start to grow from somewhere it's already being used to continue growing from that point. Okay, how's that? So after it is stopped, maybe randomly I can pick one of the cells from the network, then start doing the growth aggregation from that point. Maybe that might be interesting. Okay, and probably it's also a good idea to choose the one that has the smallest number of connections. Like if it has 2 neighbors being connected, that might be better, but if you have like 8 or 7 connections as a neighbors, you might want to avoid it. So I want to choose something that's has less connections out of these aggregational points. So to do that, I think you do need to calculate. You need to have some informations for each point, for each aggregational points, how many neighbors you have. Okay. Well, you could do that. You can just calculate that dynamically, or you can just do it. You can have it as attributes. You can calculate it as an attribute at some point. I'm not sure which one's better. Maybe it's useful if I have it as an attribute, so shall we do that? Okay, so let's try to do that, shall we? So first thing first, we need to know whether the growth has been stopped or not. Okay, so in order to know whether it has been stopped, I need to check this value here, which is the kind of a condition used in order to check whether it's been stopped or not. And this is the condition here. If it's been returned, then that means it's been stopped. So yeah, let's create some conditions for that. And I think for each tip point that I'm going to create here, now let's try with the multiple number of tip points with the current method, see if it's gonna work. Okay, seems it's working. Well, but at some point everything just stops because there are no more directions you can go. Though maybe you always want to have like 3 cells being moving around to aggregate the spaces. So in order to do that, you need to know how many points currently are moving. So let's create some ID to each of the tip point. Let's call this tip ID with I. So each tip point has some ID from 0 to 1, 0, 0 to 1, 2. Okay. And after it's been stopped, I want to change the tip point to somewhere else, somewhere in the structures, and use it as a new tip point with the same ID, with the same tip ID. Hi Raphael, don't you think about working in some VFX studio, game or movies? If I could, that sounds really fun, but I don't have that chances, unfortunately. Okay, so where was I? So so this is the conditions where we are checking whether the tip has been stopped or not. So when it has been stopped, this is where I want to choose the next structures to go. So I could write the code here. Yeah, maybe it's better because you have all the informations you need here. So when the tip point has been stopped, first thing you could do is to search for all the aggregational points, then look for the least connections, least neighbor connections, and choose that point as a next candidate for the tip. Okay, so well, I could write it here, but it's already a bit long, so maybe it might be cleaner just write it somewhere else. Yeah, maybe. Okay, so if I want to write this down to somewhere else, I need to have a additional informations. Okay, what I'm gonna do is to set point group stopped Yeah, I'll do like this. Okay. And also I need to pass the tip ID when I create a new tip. So set point attrib tip ID to like this. And for the previous point, I could make the tip ID to negative value, I guess. Because default, it's going to be 0, I think. And when it's been stopped, I can just copy tip ID to the current number. Actually, this has to be the tip ID. Okay. Oops. I got an error. Syntax error. Okay, here. Okay, so I think I have to make all the other tip ID to -1. So I'm going to create an attribute create node for all the points to make the default value to be -1. So only the tip point will have these value. Okay. Let me just check if this tip ID is going to be updated. Okay. Let's see. Check the tip. And you do have, okay. So you have, this one is the stopped one. Does it have a stop group? Nope. It's missing a stop group. That is because, okay, this needs to be 1. Okay, let's do this again. So if I have a tip points. Okay, so this one has a stopped group. Okay, that's good. So these are the alive tip points. This is the dead tip point. And for the dead ones, I can replace it to somewhere else. Alright. So let's do that. I'm gonna create another point wrangle for the stopped one. And I am going to get all the aggregational points and check this the one that has smallest connection as a neighbor. Maybe 2 or 3 maximum. If it's not available, then I can just skip it. I mean, even converting this into a live tip. Okay, so first thing first, I'm going to get the list of points, aggregational points, using expand point group, which will give you a list of points inside the AGG group. Now, for all the points, I can count the neighbor which I have already done here, so maybe it's a good idea to make it as a function. Where is it? So this is where I was counting the number of aggregation as a neighbor and free directions. So let's have this as a function so that I can reuse it somewhere else, somewhere around here. Okay, so I'm gonna create function. Well, how do I call this? Void. Find neighbor infos. Let's call this get neighbor infos. Okay, and let's the information I need is the point, which is this one. Should be replaced with this one. Okay. And also you want to have an output. In this case, the n count aggregation number, and did I need it to say out? Forgot. Export. Yeah, maybe export. Maybe. And n count free. Okay. Now I can just delete these. Okay. And let's try using this. So get neighbors info apt. This is an output parameter, so I can already have it declared and have it like these, and that will hopefully create all the value that I need. Let's just check if it's gonna work as previously. Okay, yeah, it works. Okay, so the function works. I can copy this one so that I can reuse it here. Which looks like a heavy calculation because there is a lot of loops here, so which might not be a really like performance better. It's not good as a performance, but let's just do it brute forcefully for now. So I have this function for each point that I've found as an aggregation. Let's get the information, both the aggregation neighbor count and the free count, which is both useful. I would like to have less aggregational neighbors and with a lot of free spaces to go as a next point and as a next candidate. Okay, so And let's make sure that the n count aggregation is less than 3. So you only have 2 connections, at least 2, less or equal than 2 connections. That's and that's the chance you could change the tip point to the next one. Okay, and for these n count free, maybe I can also use that. Let's say also, and n count free is more than maybe 2, more than, if I have at least 2 spaces to go, maybe I can choose that one to go for the next one, maybe 3. Not sure what's the best value for that. Okay, now I can have all the candidates in the array. Hey, thank you, Raphael, for your kind word. Hopefully that's true. Well, not sure. So this is going to be the candidate points. Okay. Now you should be able to have a bunch of candidates. Let's check that. If I really have it at the stop point. Okay, so there you are. So these are the possible points which could be for the next tip point, which has already been stopped. Okay. So for these points, I can then randomly pick one of the point numbers. If the length of the candidates is more than 0, then I can get some random value out of it. Let's create a random index. Multiply by some random value based on maybe positions or point number. Plus seed. And make it as a integer value here. Okay, now this is a newly chosen candidate, and for this one you can set this point to a new tip. So set point group tip to this candidate point with 1, and you can copy the tip index or tip ID with the current one, and that should be attribute, and you can delete the stopped group from the current one. Okay, so hopefully this condition will enable you to more of infinitely grow in the system, unless you don't meet with these conditions anymore. Hopefully that'll do. Let's see. I think it's easier to see with just one tip, so I'll reduce this to 1. Let's check how this goes. Whoa. Okay, something must be wrong. This must be the timing it stopped, but then it just grows over and over again, over and over. Now, possibly the reason is because this stopped condition is running too many times. So must be something wrong here. So okay, let's check that out. Let's see the timing when that happens. Okay, it only supposed to just grows in one direction, but seems like it's growing two-way at this point. Okay, what's wrong? So meaning, I think it means you have 2 tip points currently. Yeah, that shouldn't happen. So I need to check when does it happens. So at this point it stopped. But wait, did it? Maybe not yet. Okay, so this is where it stopped, but it still has a tip point, so maybe this is the problem. When I have set the stopped group, the tip point has to go to be 0. Yeah, right here, which I should be having here. Interesting. Other than that, let's look at the previous one. So currently this one's okay. In 83 you have a group, so okay, well this only has 1 stop, so that's fine. Wait a minute, then this must be the problem. Okay, so after all, this has some problem here. You have both stopped and tip, so it didn't really remove the stopped group right here. That's the problem. Didn't, right? Yeah, I didn't. So why is that? Okay, so this has to be PT num. That's why. Yeah, that should do it. Okay, let's see. Alright, I think it's working. It's being aggregating, endlessly. After it has found the dead end, something like this, it restart from somewhere else, which has less connections and have more chances to go in many directions. Okay, looks good. And I think this runs pretty fast on large grid as well. If I make this grid to something like 25 by 15. Let's check. The area is pretty large. Still runs smoothly. And now if I increase the number of tips to somewhere 5, at some point it connects to each other, creating some complex structures, which looks fun. Okay, everything is being connected. If you are also considering something like architecture, it might also be a good idea to create some additional weights, like gravity-wise weight. Might be interesting to do that, but let's keep it aside. Let's bring 2 types of cells to each positions. One is the closed one is the one that looks like this, opened on the hexagonal plane, which is not that hard to do. This is the original shape. For a hexagonal shape, you could open it up using polyextrude. No, you might need to define which one's which, so let's create a primitive wrangle to set a primitive group, which one's hexagon, which one's square. Just like I did here when I created a connections. I have these, so I can just copy it, and paste it right here. Instead of line, I'm going to create a group to the primitive. Okay, now I can create a hole just on the hexagon. For each individual element. Oops. Open up the hole. Okay. Maybe I might want to have some thickness to this as well. Allows thicken, create some thickness to it. Okay. Now I have the closed one and the opened one with the window. Let's have some bevel as well to make it a bit smoother on the edge. Same for the closed one. Okay. Now I can create the type attribute. I can first pack it, maybe, to make it lighter. Before packing it up, let me create a normal node to control the vertex to somewhere 3 degrees. So it becomes a bit more crisp. Okay, then I could create an attribute to each of them, something named as a type, which can be used with a copy to point group or copy to point node. So the closed one will be 0, the opened one will be 1. Okay, I'll merge it. And then place it here and use the piece attribute type. Okay, so for each point I need to set the type info, which I could set randomly or dynamically, randomly or as a post process. If I don't really need to change the type, then I can just do it as a pre-process somewhere before simulation, which is the most efficient way to do. For each point on the grid, I can just randomly choose the type, maybe by a percentage. So if randomness is point, the 30% of chance you'll get one with a hole, 70% you get one with the closed type. Maybe you might want to change the range. Okay, let's see what's happened. So, and I also want to make the color randomish as well. Maybe let's set the color here. Instead of coloring, well, maybe it's better having color as a check. So in terms of the color, I could just set it randomly here. Random from attributes, ram from attributes. Okay. I could create some color related random value, which doesn't really mean anything, but I could just use it for coloring from black to white or more colorful. Okay, so let's say I have this call attribute. I can color each point with that attribute with some ranges, something like that. Okay, let's see. Play it. Going to have a whole lot of connections like that. Maybe I want to make it gradation a bit more loose. Yeah, this is better. Oops, what? wait. Okay, my angle has been messed up. Let's fix this. What's happening? Just create the camera, reset it. Not sure what just happened. Okay, so yeah, looks good. Maybe it's a bit too big in terms of grid. Let me reduce the size a bit so that I can see it better. Easier to see. Okay, it's packing too fast, but yeah, this is pretty much I wanted to show here. As an additional process, maybe I can also animate how each cells appears, like fading in and fading out. That could be an additional process that I could add, and also maybe additional weights could be added. Let me try to animate the appearance, animate these pop up for each cell. Just for each frame it just pops as it is, but maybe I can have few frames to appear each one of the cells with some animation. Might be interesting. Okay, so to do that, I kind of have to. I can do it inside a solver, or maybe I can do it as a post-process steps after solver. I think for this case it will be easier to set after the solver, so let's do that way. What I'm gonna use is time shift. Okay, somewhere around here. And time shift can pack multiple frames in one frame, meaning you can slow down the animation or you can make it faster. If you want to make it slow down, you can divide the value by some frames you want to use for animation, let's say for 5. And you can untoggle the integer value, but make this value integer so that it will be easier to see the starting point, the starting frame, and the end frame when the animation happens. So I would say floor. Okay, so let's just see what happens. So initially you have nothing, and if you play it, it's kind of weird that it just appears two geometries at once. So maybe it's better if I just say it ceiling. Okay. In that case, it starts from 2, then using 5 frame to aggregate each cell. Okay. So for each 5 frame I want to make it as an animation. Maybe just scaling the cells to look like it's popping up. Okay, so I could, in order to do that, I could set the p scale for each point from 0 to 1. Okay. It could be linear, it could be more something using curve to make a interesting pop-up animation. Let's start with the linear animation. Okay, so what I need is these frame value first of all. So let's have it 5 here. Let's copy this so that it can sync with this value here. Okay, now what I need to do is to convert the current frame to current frame which goes from 0 to 5 to 0 to 1, just remapping the value. based on these calculations here. So this is dividing the current frame value, let's make it float, current frame value by 5 and calculating the ceiling. So let's try to do the same thing here. Current frame divided by frame ceiling, which will give you an integer value, but actually what you need is a fraction value for this one in order to convert it into 0 to 1, I think. So let's get the fraction of these divisions and see if I can just use it as a p-scale. Maybe not, but just to check. Let's see. And no. One thing that I need to do is to only make the animation for the tip point, not for all the other aggregation or stopped point. So think what I can do is to make this tip to make the p-scale, or I can check whether the current point is in tip or not. Int tip if in point group tip pt num equal to 0 or equal to 1, then you could animate the p-scale. Otherwise, set the p-scale to 1. Okay, so let's see what happens. Now something is wrong here. It's having some flash. So I can see that start from 1, but then no, looks like it's started by small number, but then at some point it goes back to 0. So that, I think, is because this fraction does not give you a value more than 1, more or equal to 1. You always get value less than 1. But in the end, you need the scale 1 in the frame. So I think that's the problem. Okay, so what you could do with these, one thing you could do is to subtract the current frame by a really small number, I think. And that way you could create, I mean, it's not really equal to 1, but you could have something like 0.99999 as the end of the value, so that might solve the problem. In terms of the animation, I guess that's fine. This could even be smaller, so maybe that's fine. Okay, so this is just a linear pop-up, but maybe I might want to make it a bit more interesting. So this f value is normalized value from 0 to 1, so I can then use a ramp parameter to control the curve for the animation. Oops. Okay, so this is the default. I can make this curved so I have some interesting animation. I don't know, like something like that. Let's see what's going on, what's gonna happen with these. Interesting, but not as I expected. this? More like a sigmoid curve. Okay. Make it slower and in the first. You could also make it bounced. In that case, you might need to have more frames to see the effect. Which might be too slow. I don't know, I mean, this is pretty much infinite possibility, so it's pretty much up to you. Why can't I delete this? Like this one. Yeah, maybe this. Okay, looks good. And let's increase the tip, and I am going to add additional weight, maybe based on the gravity direction, to the y directions. Let's say it goes, it's more possible to go downward than going upward in terms of the gravity. Let's say I have that kind of conditions. So going back to the aggregation code, let's see where I was calculating the weight. So this is where I have the weight here. So I can add as much weight as possible. Additional weight that I could have is based on the neighboring, I mean the direction where I'm going to the next, going to aggregate next. This is the neighboring positions, right? So I could calculate the direction going from the current point position to the goal. Okay. Now let's normalize this, and I can calculate how much percentage it's going down or going up by calculating the dot product between the direction and, let's say, upward, the y direction. If this value is equal to 1, then that means you're going up. If it's -1, then it's going down. So based on this d, I can create some additional weight. Fit 1 dot. So if it's -1, I want to have more chances to go. So let's say 0.7 or 0.8. If it's going up, 0.2. How's that? So 80% of the time it wants to go down. Okay, so now I'm going to multiply this to the final weight. And hopefully that will create a weight that eventually goes down most of the time. Not really sure if that's the case, but most of the time. What I'm hoping to get is more dense structures on the bottom, a bit scarce structures on the top, which looks like an architectural structure. And I think that's what's happening here. Yeah. Okay, so this is it. I hope you liked it. I think I'm done with today's live stream. I hope you liked the live stream that I did today. The topic was pretty simple. Maybe a lot of you guys found it too easy, but hopefully some of you guys found it interesting. It might be. I mean, the grid itself is pretty interesting. I think it has a lot of possibilities in terms of the structures. So just by replacing these cells to something else, it could become really interesting, I think. Because you just need to think about the connections for each faces, and just by replacing these faces to something else, you could still use it as a structure with the same definition. Well, I could give you one example. For example, if this one, the connection thing, you could actually transform it to make it half size so that it will fit within the structure, and you could, I don't know, like do something like poly wire have enough divisions. Let's normalize this. The size might be a bit weird here, but what I wanted to say is that you could just replace it with these and use it as one of your cells. And if you combine the idea with something like wave function collapse, you could add multiple number of cells for each point to create the structures, which is again interesting. So in terms of the three-dimensional wave function collapses, I might want to do it sometime. Yeah, because it's a really interesting topic, just as you see in Townscaper game, which looks really great visually and algorithmically. That things I want to try myself as well. Okay, so this is it. Let me know if you have any questions. If not, I will end this live here for today. Thank you for coming, and hopefully you can come next week as well. I'm gonna upload the files to GitHub, and you can access to it from the video description page later. As always, feel free to use it for your own purpose. Okay, this is it. Thank you, and good night. And thanks for all the comments. Right. Night. Thank you, Sarhat. Thanks for your kind comments. Night.